Thank you, Chris. So this is my dull title slide, but that's what I should have put up. This is, of course, what we do to undergraduates who don't pass the exams. I'm going to talk to you today about the story of an undergraduate project. How to get this through the UCL mailroom. In our UCL Maths degree, a small subset, but a highly prized subset of our students do a fourth year and come out with a Master of... It is a Master of Science, but it's not an MSc, it's an MSci, a 4-year undergraduate programme. And in that final year, they get a quarter of their credit for an individual research project, which is done in close collaboration with a single supervisor, single student. And a few years ago, I proposed one on how the chocolate fountain flows. A student came to see me, and he said, is there any chance of doing some experiments on this one? And I said, well... So we started just before the summer, and it runs through till May. I said, well, we'll look at how it's going. And if it's going all right by Christmas, yeah, we'll get a chocolate fountain and you can do some experiments. So we got to the run-up to Christmas, and it was going superbly well. He'd found loads of useful literature. He was doing great calculations. There was nothing to complain about at all. So I duly went on Amazon and bought a chocolate fountain. Got it delivered to the department. I get a snotty phone call from the mailroom going, somebody is getting their Christmas presents delivered to work. This is not allowed. And they wouldn't deliver it. Had to go down to the mailroom and fetch the damn thing. Anyway, the key thing that the chocolate fountain project was about is mathematical modelling, and that's what I want to talk about primarily tonight. There's two elements of it that you can model, the chocolate and the fountain. So let's talk about the chocolate first. So I've got a quote here, which is from the British Society of Rheology Bulletin. Notably, it's a report from the Chocolate Congress 2010, and I don't think it's well enough known that there is such a thing as a chocolate congress. Anyway, molten chocolate is a complex material. It's a highly dense suspension of sugar and cocoa solids in a cocoa butter liquid phase, complicated by the variation in the composition of cocoa butter with source and harvest. There's a lot hidden in that. So the sugar solids are crystal-shaped. If you heat it up and cool it down again, they become uniform-sized crystals. If you don't do that, they are a wide range of sizes. The cocoa solids are shaped by whatever you did to get them into the chocolate in the first place. They are solid at any temperature that you would sensibly ever take the chocolate up to, so they maintain their shape whatever. And this cocoa butter thing, it depends on the rainfall. So 1 year's chocolate is not the same as the next year's chocolate, even from the same manufacturer. So anything I show you where I say, this is what chocolate does, what I mean is, this is what one person's sample of chocolate did on one particular day. It's always much, much more complicated than I'm going to tell you. But suppose we've got a little bowl of molten chocolate. How will we describe it? What do we need to know about it to be able to use it in models? Well, what one typically does as a rheologist, which is someone who studies the deformation and flow of matter, is impose a shear flow, which is the thing I've got on the board. You put your sample between two plates and you move them parallel to one another. You measure the force that you have to impose to cause this flow, and that measurement tells you about your sample. So, in fact, if you measure the force per unit area that you're having to apply sideways, that's called a stress. And then the stress divided by the rate of strain, which is simply the velocity of the top plate divided by the gap, that gives you the viscosity of the fluid, a measure of thickness. So the thicker the fluid is, the harder you have to push to get it to go at a given speed. What you do in reality, because if you do that, you can't get a steady flow going for very long before one plate's gone off the other plate and your sample's on the floor, is you put a cylinder inside a very slightly larger outer cylinder, and you put your sample in between. And that way, if the gap is thin, you can get something which very closely approximates a perfect shear flow and which can be continued indefinitely. This thing is called a Couette rheometer. It was invented, as you might imagine, by Couette, who built his first one to measure the viscosity of air, which is pretty thin. So it was very, very finely calibrated. So you measure it, and then what I've got here is a plot of the stress which you remember I said the viscosity was just the stress divided by the shear rate, the rate of flow. If you plot that stress against the shear rate, then we have a variety of different generic ways the fluid can behave. And I'm going to talk about each of them in turn. So the first one, the stress is proportional to the shear rate. That means your viscosity is a constant. That's called a Newtonian fluid, and it's the most common fluid model and the most common fluid. So a variety of common fluids are this: water, not babies; wine is a Newtonian fluid; oil, not disgusting mucky oil like that, but clean oil is, to a good approximation, a Newtonian fluid; and gases are also Newtonian fluids. So you can imagine, with water and air in this model, there's quite a lot of really important climate stuff based on using the Newtonian fluid model. There are thousands of people all over the world doing research in Newtonian fluids. But I want to talk about the niche stuff that isn't Newtonian fluids. So here's one. If the stress increases more than linearly with the rate of strain, that means the viscosity increases the faster you go, which we call shear thickening, because you apply extra shear and it gets thicker. These are fairly rare. There's only 2 or 3 examples known. And the one that you'll be familiar with is cornstarch. So if you take corn flour and mix it with water, the bit that you do just before you stick it in the gravy, you get something that behaves quite oddly. If you stir it slowly, you can get it to flow like a perfectly ordinary liquid. But if you stir it quickly, you can get shatter patterns from it as it solidifies under the action of fast shear. So that's an extreme of being more viscous, is being so viscous that it actually acts like a solid. And this is where the custard of my title comes in, because custard powder is nothing more than corn flour with a bit of yellow stuff and sugar and flavouring stuck in it. So I have genuine research in this area. So if you take this strong shear thickening, actually, if you measure it properly in a rheometer, it's not a smooth, steady increase, such as I drew in my cartoon diagram. It's much, much sharper than that. So you can see here, this is viscosity plotted against shear rate. And as you increase the shear rate, the viscosity suddenly leaps. And if you can't quite see the detail, this is a log scale. So in almost no discernible distance in change of flow, I mean, that's also a log scale, but that's less important, you get a multiplication by over 10 of the viscosity. So this stuff thickens up and jams incredibly quickly when you flow just a tiny bit too fast. There is also a continuous shear thickening thing where it thickens slowly, and that happens at lower concentrations of solids. But when you get close to the jamming concentration, the amount where you've got so much solids in there you simply can't get any more in, you get this discontinuous shear thickening. And there's a load of research going on about it, and it's not fully understood. What we do understand about it is that it never happens. So I say understand, but this is largely empirical. So it never happens if there are attractive forces between the particles. They tend to agglomerate, you don't get this phenomenon. You have to have some kind of repulsion if 2 particles get close together. There was an early theory that included clusters forming, but that doesn't get you enough viscosity. There was another early theory to do with dilatancy, which is the phenomenon where, you know, if you step on wet sand and then you look where you've just stepped, it's dry and then refills. This is because as you impose a deformation on a closely clustered group of spheres, actually they have to, they come out of their close packing because you've deformed them, and so they take up more volume than they did, and they suck water in. So when you step on the sand, you're actually causing it to rise up, and the water gets sucked down, which is why it looks dry. That looked like a really appealing candidate, and it does predict this discontinuous shear thickening, but it also predicts discontinuous shear thickening for some situations in which we know it doesn't really happen. So that's too strong a mechanism and therefore also can't be right. The thing that seems to be working now is contact between the particles. So there's fluid flow, but also contact, and this contact needs to be frictional, and the friction needs to only get turned on if the forces pushing the particles together are strong enough. When you put all of that in, you can now in a simulation, generate discontinuous shear thickening. My contribution to this thing, so I've been looking at contact since well before anybody got excited about discontinuous shear thickening. I just happened to be there before it all got hot. And I worked out what effect contact would have on a dilute suspension, so that's just a few sand grains in your water, and showed that actually contact makes the viscosity go down a little bit, and friction makes the viscosity go up, but so weakly it's almost not measurable. And then for moderate concentrations, friction does increase the viscosity, but not much. And then when you put in hard contacts with this criterion for the friction only comes on above a certain force squeezing together, we found that we didn't get the discontinuous shear thickening that everybody else was getting. And our only guess for why that is that we were very carefully tracking the distance between particles, which other people don't do. And so we are suspicious that actually you need your particles to be slightly squishy as well, and that's an extra ingredient. But we're now working on creating new models that incorporate the microstructure that forms in shear flow as well as contact, and aiming to both capture this shear thickening, but also the bizarre stuff that happens if you suddenly reverse your shear, where the viscosity, the apparent viscosity, drops very suddenly as you release the jamming that you'd been building. Right, that's enough on custard. Oh, except for why do we care? What do we use it for? So there's a chap in Delaware, I think, it'll be in the transcript, who has treated Kevlar with essentially cornstarch, something very similar to cornstarch, and made it far, far more effective as ballistics protection. So with this impregnated Kevlar, you can stop a bullet at point blank range in a way that you just can't with pure Kevlar, which is astounding. And then the reason that we actually got into it is that we found a company who want to do cryopreservation. Now, this is the freezing of organs, cells, whatever, and the bringing back to life after storage. It's a beautiful technology. It works really well for anything as big as an embryo. But it doesn't work for anything bigger, because the thermal stresses when you're defrosting are too great. And while you're doing the slow defrost process, ice crystals, which are nucleated during freezing, grow and destroy your cells. We would love to be able to freeze things without nucleating ice crystals on the way down. And the theory is that if we can get cornstarch into the cells, and cornstarch is pretty biologically neutral, it's not damaging, it may be possible to, by shearing, cause some sort of vitrification within the fluid inside the cell that impedes the nucleation of ice crystals. And if we can, then it can be brought down to the low cryopreservation temperatures without the crystals existing, and then it can be sheared again on the way up. Hopefully, who knows, we may then eventually be able to freeze larger things. And I'm not thinking kidneys, I'm thinking corneas, still very thin, still a chance for the cornstarch to diffuse in and out, but still an awful lot bigger than an embryo. Right, that was one fluid. The next one, the green line. So this one, you'll see that there are several degrees of finite stress for which you don't get any shear rate at all. In other words, if you apply a small amount of force to this thing, it's not going anywhere. And we call that a yield stress fluid. Examples include whipped cream, ketchup, as you know. If you just hold the ketchup bottle up, nothing happens. And toothpaste. The toothpaste yield stress is quite important because it's the thing that stops it from running when it's sitting on your brush. It's not important for what the toothpaste does, but it's really important for whether it looks right and whether it feels like toothpaste. So I have a research project on toothpaste funded by a toothpaste manufacturer who I won't name here. It's a really, really complex fluid. So the base of it is a polymeric fluid, but you also have two different kinds of silica particles, roughly roundish ones, which are there to make it thicker, really, really jaggedy shaped ones, which are there to clean your teeth, and a whole load of active things, none of which seem to make any difference to how it sits on the toothbrush, but which are all also very important. I have named the toothpaste manufacturer, it turns out, GSK. So we've got a group going on, working on experiments with controlled suspensions that are not quite as complex as the toothpaste, working on mixing problems involving the polymers and the particles, and we've also been looking at modelling to see what effect adding particles to the viscoelastic matrix will have on how you process it. With the aim in view being to make sure that the process always produces something that does have that yield stress, because often their processing produces a liquid that would do the job perfectly well, but nobody will buy it because it doesn't sit right on the brush, and so they have to bin it. Right, and then the final kind of fluid that I put on my list is the one where the viscosity decreases as you increase the shear rate, and these are really common. These are shear thinning fluids. So paint is shear thinning. By design, you want it to sit on the brush and not dribble, but when you get to the wall, you want it to flow very easily without a huge amount of work. For the same reason, nail polish. Lava has almost exactly the same rheology, but obviously not by design in the same way. And the reason that it's here, chocolate. Chocolate is a beautiful example of a shear thinning fluid. This is now not stress against shear rate, but viscosity against shear rate, and you can see it decreases. You can also see, if you've got good eyesight, that white chocolate is thicker than milk chocolate is thicker than dark chocolate, but that's not particularly important. These are all taken at 40 degrees, seems to be the standard chocolate temperature. It's also the temperature that our chocolate fountain runs at. So, how do we model that? I've got three models that are the three models most commonly used in the literature. The first one is a Newtonian fluid. So the stress is just viscosity times shear rate. The viscosity that we are going to take is about 14 Pascal seconds, and for reference, water is 3 orders of magnitude smaller than that. The next one is a power law fluid with parameters here. The N, the power that goes with the power law, is a third. So our viscosity decreases like a cube root. And then we have Casson's model, which, as you can see, is substantially more complicated than the other two. This was, in fact, the recommended model of the International Confectionery Association from 1973 to 2000, at which point they noticed that this bit only really makes a difference at very low flow rates, and the model isn't very good at very low flow rates. So you're doing all this complication for very little gain. So at that point, they ceased to recommend it as their optimal and said, we recommend that you just use an empirical model instead, which means essentially use a power law, and if you really need to, use two different power laws for different flow rate regimes. So I'm going to forget about Casson's model and just go with these two for the rest of the talk, the Newtonian fluid and the power law fluid. The power law is a better fit. The Newtonian fluid is very well understood, very easy to work with, and it's nice to have two models because then you can compare the effect that the shear thinning has. So, I've modelled the chocolate, now let's model the fountain. This is what our fountain looks like when it's not wearing its chocolate. And you can split it into three regions: the upflow in the pipe, the cross flow down the dome, and the freely falling curtain. Let's look at the pipe first. This is what's really going on, except vertically. There is a screw turning which pushes the chocolate up. Now, modelling that is well outside the scope of an undergraduate project. It's a fully three-dimensional flow. You'd have to do it with full-on computational fluid dynamics. So instead we go, let's just suppose that we're imposing a pressure at the bottom and let that do the pumping. And that's a really nice starter problem for the student to get a handle of how the equations work and what you can do with them. So these are our governing equations. This is the simplest fluid flow equation there is. It's basically a continuum version of F equals ma. So there's our governing force. We have mass times acceleration, or in this case, because I've made it per unit volume, it's velocity times acceleration. And I've got a pressure gradient which goes with the body forces. Those are all the forces acting. That's just simple ballistics. But then you have to put in a viscous term to account for the fact that your fluid objects to being made to flow. So this is now a dissipative equation. So we have a viscosity term and all of the terms we had before. And then that's true for a Newtonian fluid. If you want to generalise it to any complex fluid, you simply put in the divergence of a stress tensor there and leave what that stress tensor is to be specified by some extra equation to be added to the system. So now here are my full equations. I'm not going to spend very long in here, but these are now in cylindrical polar coordinates because that's the appropriate coordinate system to use for a pipe. And what I want to do with them is simplify them. So first of all, I'm going to assume that my flow is steady. That allows me to throw away those red partial d by dt terms. Then I'm going to assume that there is no radial flow, so my flow is all just straight up the pipe. That allows me to throw away everything else in red. Next one, I've got the bottom equation tells me that d by dz of uz is 0, so uz does not depend on z, which tells me my next red term is 0, so I get rid of that one. Then my stresses are generated by the velocity. So if all my velocity components only depend on radius and not on height, so do my stresses. That gets rid of another couple of terms. What about the body forces? Well, they're gravity, and we know where gravity is, so let's just explicitly put that in. That tidies us up a bit. And now we need a little bit of actual fluid assumptions. So I'm going to now say something. All of this is true for any fluid going up a pipe. But now I'm going to tell you something about what I believe about the chocolate. I'm going to assume that it is just governed by viscosity. So it is not a viscoelastic fluid. It doesn't behave like egg white or shampoo in having a certain bounciness to it, or indeed toothpaste. So I make that one constitutive assumption, and that throws away quite a lot of other terms. And then I'm left with not much, actually. I solved the top one of those equations because it was so short, substitute the answer in here, and one simplification, stick those two terms, which are just numbers, together and give them a name, and I have something I can definitely solve. So just by working through my simplifications one by one, I come to a nice simple equation, which is why I said this was a really nice starter problem for the student. They can work their way through this quite simply. You end up doing an integration, applying a boundary condition, and solving, and before you finish, you know where you are, you've actually got the velocity as a function of radius. So let's plot it. This is what it looks like for the shear thinning fluid with n equals a third. And for reference by the side, that's what it looks like for a Newtonian fluid. So you can see, they both have the same, this is plotting velocity across the pipe. So that's the pipe wall, that's the middle, that's the wall again. You can see they both have their maximum velocity in the middle, as you would expect, but the Newtonian is much more pointy. This thing has quite a large region that has approximately the same velocity in the middle, and then these shear regions at the walls where almost all of the activity happens, and that's where the viscosity is lower. Essentially, you've got a high viscosity plug that's going up with a lubricating region either side. Right, so that's pipe flow. Dome flow. I'm going to do the same thing again. This time I'm going to pretend that it's not a section of a sphere. I'm going to pretend it's just a section of a cylinder because it's just a bit cleaner. So we're imagining a cylindrical dome with chocolate coming down both sides. So I'm going to make the same simplifications as before. I'll assume it's steady. I'll assume that the flow variation is all within the plane. So my flow's all going down and not that way along my cylinder. Steady flow, flow variation and flow are within the plane. I know which way gravity is pointing. All of that. After I've done all of that, these are my equations. So I have no other terms to throw away. So what do? Well, this is where the beauty of the dome becomes visible, because this is now an introduction to a key thing that distinguishes applied mathematicians from either engineers or pure mathematicians to reach in the two directions. If you give an applied mathematician a problem, they go, how can I scale it? What terms can I throw away? Except there's one step in between. So this is the constitutive equation, constitutive assumption that I made last time. As you can see, quite a few of my stress terms are going to turn out to be 0. So I should get a bit of simplification from that. I do, but they're all in the same equation. So that just means I throw away one of my equations. Every single term in that equation is 0. That doesn't help us at all. So I'll get rid of that. Now I want to say, I want to do some scaling analysis. I want to throw something away, not because it's 0, but because it's smaller than the thing next to it. So how am I going to do this? My film is much thinner than its length. So if I have something that scales with a length of the radius of the dome, I'm going to call that scale R. If I have something that scales with the thickness of the sheet, I'm going to call that scale capital H. And I know that capital H is much smaller than capital R. So if my velocity along is of order capital U, and my velocity up and down is of order capital V, then I can scale all these things, and all my hatted quantities have to be order 1. And then I just take one of my equations, this equation, and I look at this term. This has a d by dr. That's how much does it vary as I go through the depth. So that's a 1 over h. Then I have r, that's a radius, so that's just an r. And ur is whatever it is. du theta by d theta, well, a d by d theta is not a dimensional quantity. Theta is going from 0 to pi by 2. It's not a length. So this is just of order u theta. And then I use the critical fact that if I add two numbers together and the answer is 0, they have to be the same order of magnitude as each other to tell me that these two quantities are the same size, which then tells me that the cross-stream velocity is much smaller than the along velocity. Using that and similar arguments, I can throw away all of those red terms, not because they're 0, just because they're unimportant. And suddenly things start to look quite a lot better. I now only have two equations, and they are both just a balance of gravity and fluid stresses. Now, this is a universal procedure that happens anywhere you have a thin film flow. It doesn't depend on the nature of the chocolate. It doesn't depend on the geometry of your surface, actually. The only place that the geometry is left is in the direction of gravity. So it would be just as good on a planar slope as on my dome. And that has applications in lava flow, for instance, where a lava sheet flowing down a mountain is typically much less deep than it is long. Painting flows. The tears in the eye, every time you blink, you're doing these thin film flows. And you can solve it for our two fluid models. You don't need to look at the details of that, but the velocity profiles are there. Again, you see this phenomenon that it's a bit flatter with the power law than it is with the Newtonian fluid. For comparison, I've put below the ones we had in the pipe. The Newtonian one is exactly the same curve. They're not quite the same for the power law curve, but they're very similar. We can also predict the film thickness and map it onto actual experiments. That's what the two shapes look like, assuming that you have the same total flow of chocolate in both cases. And that's what it looks like compared to reality. To be honest, I think the most serious thing that's happening there is that the dome is not a perfect segment of a sphere. So we had a go. Finally, the falling sheet. Now, this is a much, much harder problem. There's two free surfaces, one on the outside and one on the inside. You don't know where the whole sheet is. You don't know how thick it is. You don't know where it is in space. But also, you don't know the boundary conditions to use at the top of this flow. And the reason for that is what's called the teapot effect. This is, as you might be able to tell, a beautiful diagram from a paper that goes back to the days when departments used to have draftspeople to do their diagrams for them. It could be something like this that happens at the corner of the dome, or it could be something like that. And the difference between those two is not anything to do with the shape of the dome even, which we could theoretically measure, because the only differences between those teapots there is that somebody's put different chemicals underneath the lip of the teapot. If you rub the bottom of the teapot with carbon black, it pours off beautifully, but you do get carbon black in your tea, which is obviously not ideal. So the teapot effect is an absolute nightmare for trying to work out what to do with your chocolate. So we decided to just ignore it completely. we don't know what it is. Well, basically, you need chemistry, and I don't have chemistry, and my student didn't have chemistry either. So between us, we decided we'd just gloss over that bit and just start from just after the top of the sheet. So the falling sheet, turns out the theory you need is the theory of water bells. These are water bells seen in a garden centre, but you can build them very easily in your kitchen. If you take something horizontal, and our favourite is a pencil vertically embedded in something with a coin blue tack to the top of it, and then put it under a running tap, the water sprays out in all directions. But it doesn't just spray all over you, it actually comes round as it falls. And this bell shape is exactly what the chocolate fountain is doing. Here's a better one made in somebody's lab. So as you can see, the water impinges and then it comes round, and you've got an interior flow and an exterior flow. You have to worry about what the air's doing on the inside as well as what the fluid's doing on its way down. But essentially, there aren't actually that many forces going on. There's the pressure difference between inside and outside, there's the surface tension, and there's gravity. Now, in our case, it's remarkably difficult to get a chocolate fountain to flow steadily in such a way that there is genuinely a difference between inside and outside, rather than them being constantly briefly connected to each other and equalising their pressure. So I don't really believe in that term for our flow. I think we just have surface tension and gravity going on. Using that and converting somebody else's numerics with our flow rates and our viscosities, and returning only to the Newtonian fluid, because this is now getting too complicated, we are able to predict a shape for our falling sheet. And while it's not brilliant, it's not bad as a fit for the real chocolate fountain. So that brings me to the end, or almost to the end, of what I want to say. I should thank my group. Adam Townsend was the undergraduate student who did the chocolate fountain project. He was also a PhD student who worked on the custard stuff. Leah Mescott is a current PhD student who's working on the toothpaste. Urian Gillison is a postdoc working with me on the toothpaste stuff, who's also done stuff relevant to the custard. And I will show you the paper, because we have a proper peer-reviewed paper that came out on this. Now, you may not be able to quite see this, but it's been downloaded over 20,000 times in its first 2 years of life. For context, one of my more normal research papers, I was sent a certificate when, after 6 months, it had been downloaded 300 times. It also went viral. So we were in the Daily Mail, which is not usually a good thing, but this time I'll let it off. And we were even in the Washington Post with my favourite headline. Someone finally looked into the physics of chocolate fountains, because we'd been waiting for that. So in conclusion, the pipe flow is a really good starter. Dome flow has this universal structure to it. The falling sheet is dominated by surface tension, so it's just a circular cross-section, has two circles, both of whose surface tension is pulling them into the middle. That's the reason it falls inwards rather than straight down. And the top of the falling sheet is governed by the teapot effect. Chocolate itself is a nightmare, but it does get the media attention. Thank you.